imagine staring at, like, a completely black terminal screen.
Oh, the worst nightmare.
Great. Your main production server just crashed hard, taking the entire database with it, and your only lifeline is a single backup file you created yesterday.
Talk about stressful.
Yeah, totally. So we're diving directly into the Linux Data and Survival Guide today to equip you with the exact skills to handle that exact catastrophe.
And, to help you dominate your ethical hacking and Linux Plus certification exams while we're at it.
Exactly. So if you're following along with the visual companion, go ahead and pull up your deck. We're moving step by step through the material right now.
Let's kick things off with slide 1, titled The Operator's Manual, Linux Data and Survival.
Right. Our core mission here is really mastering archiving, cloning, and backing up data.
Because in the real world,
And on those certification exams, yeah.
right, treating data correctly isn't just about saving hard drive space, is it? No, not at all. It is quite literally about survival. I mean, it's about security, preventing corruption, and having absolute exactness when you move information from one place to another.
Okay, so let's jump straight to slide 2, titled Step 1. Know the difference between packing and shrinking. The visual here shows the archive tool, tar, as a cardboard box, right? While compression tools like Dzip, BZIC2, and XE are represented as like a vacuum seal bag.
Yeah, which implies they do totally different things.
Even though people use the terms interchangeably all the time.
All the time. But it's a vital distinction. Archiving is just bundling. Compression is mathematically shrinking.
Okay, let's unpack this. So if I'm moving houses, tar is me sweeping all the loose pens, paper clips, and sticky notes off my desk.
Just throwing them in a box.
Right. Dumping them into one single cardboard box so I only have to carry one object to the truck.
But the box doesn't make those items weigh less.
Exactly. The vacuum seal, the compression part, that sucks the empty space out to make things physically smaller. But my question is, why does the slide explicitly say operator rule number 1 is to always pack the box before you vacuum seal it?
Right, like why not just vacuum seal the loose pens?
Yeah. Why can't I do that?
Well, it comes down to how Linux file systems handle metadata. A file system doesn't just store data.
What else is in there?
It stores complex folder hierarchies, permissions, ownership records, symbolic links, all that stuff. A raw compression algorithm doesn't understand any of that.
Oh, interesting.
Yeah, it just looks for repeating byte patterns to shrink. So if you point a tool like Gzip at a massive directory, it doesn't intuitively know how to flatten that complex tree into like a stream of data.
So it just panics.
Pretty much.
Hmm.
By using tar, which stands for tape archive, by the way, you translate that complex folder structure into a single continuous stream of bytes.
Oh, I get it. So you create one .tar file, handing the compression algorithm one single neat target to shrink down.
Exactly. You give the system one job at a time.
Makes total sense. And that brings us to slide 3, titled tar, the ultimate cardboard box. Let's look at the syntax here. It's tar-cvf archive.tar/home/user.
Quite a mouthful.
Right. It seems so tedious to type those specific letters every single time. Like, why are these flags separate instead of just having a zip button?
Because Linux is built on the philosophy of absolute modular control.
Yeah.
You're building a custom tool on the fly.
Okay, so break down the flags for us.
Sure. So the -C stands for create a new archive. The -V is verbose, which just tells the system to print out the names of the files on your screen.
So you can actually watch it happen in real time.
Right, exactly. And then -F stands for file, telling it to output to a specific destination rather than, say, a physical tape drive.
But looking at the slide, there's a strict rule here about that dash flag.
Oh, yes. And it's highly tested on exams. That -F must, without exception, be the very last flag before the actual final name.
Why is it so strict?
Because the command parser is literal. If you type -estvc archives.tar, the system will fail.
Because it thinks the file name is the letter V.
Exactly. It thinks you want to create a file name. It has to be -cvf archive.tar.
Wow. Okay, really good to know. But let's look at the big warning on the bottom right of slide 3. It says, spot the fake. The exam is going to offer you extract as a command option, like extract-xcvf.
What's fascinating here is how incredibly common it is for people to fall for that.
I mean, it sounds totally logical.
It does, but extract is not a real Linux command for opening archives. To unpack your cardboard box, you have to use the exact same tar command, but you swap the -C for a -X.
So create becomes extract.
Exactly. You must use tar-X.
All right, don't fall for the fake, folks. Let's move over to slide 4, titled The Shrinker Matrix, Compression Algorithms. So we have our cardboard box, and now we're shrinking it.
Right, the vacuum seal.
The slide details 3 main tools. gzip uses the -z flag and gives a .gz extension. bzip2 uses the lowercase -j flag in a .bz2 extension, and igz uses the uppercase -j flag with a .xe extension.
That's the lineup.
And the slide notes igz provides the best compression. So I have to ask, if igz is objectively the best, why are we still wasting time memorizing gzip and bzip2?
Well, it's all about resource trade-offs. And really understanding the math beneath the surface. gzip uses an older algorithm called LZ77.
Which does what, exactly?
It basically acts like a sliding window, finding repeated words and replacing them with a tiny reference pointer. It's incredibly fast and uses almost zero RAM.
Okay, and bzip2?
bzip2 uses the Burrows-Wheeler block sorting algorithm. That's a fascinating mathematical trick that literally rearranges the characters in your file to group similar characters together.
Wait, it rearranges the file?
Yeah, temporarily, making it much easier to compress. But it takes longer.
And why add xe?
So XZ uses LZMA, which builds massive dictionaries of patterns. It gives you the smallest possible file, but it requires a massive amount of system memory and processing power to calculate.
So there's the catch.
Right. If you're on a legacy server with limited RAM and you need a log file compressed instantly, XZ might actually crash the server.
Yikes.
Yeah, while gzip will handle it flawlessly.
That makes total sense. You really have to know your environment. But direct your attention to the exam focus box at the bottom of slide 4, the -k flag. Keep.
Oh, this is a big one. By default, when you compress a file in Linux using these standalone tools, the system assumes you just wanted the smaller version.
And it deletes the original.
It automatically deletes your original uncompressed file to save space.
That sounds absolutely terrifying if you aren't expecting it.
It's a rude awakening, for sure. If you want to keep the original file intact while generating the compressed version, you must explicitly demand it using the -k flag.
Like bzip2-k.
Exactly. That specific behavior trips people up constantly.
Let's bring these pieces together on slide 5, titled Combining Forces, the Ultimate tar commands. The top half shows packing and shrinking in one fluid motion. tar-czvf.
Create zip verbose file.
Love how that lines up. And the bottom half shows the extraction process. To open a compressed archive, you use tar-xzvf.
Extract, unzip, verbose file.
But notice the extra detail on the right, the uppercase -c flag.
Right, the destination change.
Yeah, how does that work?
Well, if you just run the extract command, it dumps all the unboxed files right where you are currently standing in the terminal.
Which could be super messy.
Very. If you want to throw those files into a completely different folder across the system, you append -c followed by the path, like /home/accounting, to the very end of your command.
Got it. Oh, and I see another exam trap on this slide regarding flags.
You'll see distractor flags on the multiple choice questions all the time. They will throw in commands like tar-cgvf or tar-cbvf.
Trying to trick you into thinking G is for gzip.
Exactly. The G and B flags don't exist for this purpose. Just ignore them entirely. And critically, remember that the unzip command in Linux is specifically and purely for Windows-style .zip files.
So no using unzip on a .tar.gz file.
Absolutely not. It will fail.
Good to know. Okay, turning to slide 6, DD, the exact cloning machine. The visual is wild. It looks like a giant 3D printer for hard drives.
It's a pretty accurate metaphor, honestly.
I have to challenge this concept, though. If I want to back up a drive, why can't I just use the CP, like the copy command? I use it every day. It copies everything. Why introduce an entirely new, complex tool like DD?
Because CP relies on an abstraction layer called the file system.
Okay.
When you use CP, you're politely asking the operating system to read a file and write a copy.
Yeah.
But what if a file is currently locked by a database?
It would just skip it, right?
Probably. Or what if it's hidden by a rootkit? Or what if you need to copy the master boot record? The invisible instructions that tell the drive how to start.
The CP command can't see those things.
Precisely. It only sees what the operating system lets it see. DD operates beneath the file system. It doesn't look for files at all.
What does it look for, then?
It looks at the raw, physical blocks of the disk itself. It reads the magnetic state of the source and makes a byte-for-byte exact clone on the destination.
Oh, wow.
Yeah, it copies the hidden files, it copies the locks, it even copies the empty, unallocated space.
And the syntax is totally alien compared to normal Linux commands. Like we have if equals, which stands for input file, where to read from.
Right.
We have OF equals for output file, where to write to. And BS equals for block size, defaulting to 512 bytes.
The golden rule here for the exams.
Yeah.
If a scenario ever asks for an exact copy, a byte-for-byte copy, or cloning a partition for forensic evidence, the answer is always DD.
Period. Okay, let's move to slide 7, CPO, the data conveyor belt. We've got a factory conveyor belt visual here, which looks like a massive conceptual shift from TAR.
It really is. If TAR is you walking around a room grabbing files to put in a box, CPIO is you standing completely still at a packaging station, while another program acts as the conveyor belt, delivering specific files directly into your hands one by one.
Because CPIO actually doesn't know how to go look for files.
Exactly. Has no idea.
So how does it get them?
It requires a list of files to be physically fed into it using standard input and output redirection.
Like the arrows in the terminal.
Yes.
Yeah.
We're talking about using the pipe symbol, the vertical bar, or the less than and greater than arrows. CPIO operates in 3 main modes.
Okay, let's hear them.
The -O flag is copy out, creating an archive from the data flowing into it. -I is copy in, extracting an existing archive. And -P is copy pass, which takes a list of files and copies them directly to a new directory without ever making a middleman archive file.
Okay, let's see this in practice. Slide 8, CPU in the wild. Exam scenarios. This walks through 2 actual scenarios to cement this conveyor belt concept.
These are pulled straight from the quizzes, yeah.
So scenario 1 is extracting specific files. The goal is to restore only .cfg files from an archive. The command shown is cpio-ivd, quote, star.cfg, unquote, less than sign, /mnt/configs.cpio.
Let's break down that pipeline. We use -I for copy in to extract and -V to see it working. The -D flag is crucial. It tells CPIO to rebuild the original directory paths so your files don't end up in a disorganized pile.
Right, keep the folders intact.
Exactly. Then we use the less than symbol, the left pointing arrow, that literally redirects the contents of the archive file into the CPIO command's waiting hands.
And the star.cfg part.
That string tells it to only accept items matching that exact extension.
Awesome. Scenario 2 is archiving from a list. The goal is to back up configuration files straight to a USB drive. The command is ls/etc/star.confpipe CPIO-OVD greater than /dev/SDB1.
This perfectly illustrates the conveyor belt.
Yeah.
The ls command generates a list of files. That vertical bar, the pipe, takes their raw text list and drops it onto the belt, feeding it into CPIO. We use -O for copy out to create the archive. Then, the greater than symbol, the right pointing arrow, pushes the final bundled output directly onto the raw flash drive block device at /dev/SDB1.
It is a continuous flow of data from left to right.
Literally a conveyor belt.
This brings us right to slide 9, the backup battle matrix. We're looking at a timeline visual for enterprise backups. On Monday, we do a full backup. It copies every single file on the server. Safe, but incredibly expensive on storage space.
Backing up an entire multi-terabyte enterprise database every single day is completely unsustainable.
Yeah, you'd burn through hard drives instantly.
And completely choke your network bandwidth. That's why we rely on incremental and differential backups for the rest of the week.
Let's break down the math on that. An incremental backup only backs up what changed since the last backup of any kind.
Right.
So Tuesday's incremental only saves what changed on Tuesday. Wednesday's only saves what changed on Wednesday. But a differential backup copies everything that has changed since the last few all backup.
Yes, that's the key difference.
So Thursday's differential includes the changes from Tuesday, Wednesday, and Thursday. If my database changes by 10 gigabytes a day, by Thursday, my differential backup is 30 gigabytes. Why use differential if it just keeps ballooning in size?
It's a calculated trade-off between backup speed and restore speed.
How so?
Well, incremental is really fast to back up each night, but think about the recovery. If the server explodes on Thursday, to restore it, you have to load Monday's full backup, then Tuesday's piece, then Wednesday's piece, then Thursday's piece.
Wow, that's a lot of steps.
And if even one of those links in the chain is corrupted, the rest of the data is totally useless. Differential takes more storage space, but restoring is bulletproof.
Because it's fewer steps.
Exactly. You just load Monday's full backup and then slap Thursday's differential right on top of it. 2 steps, and you are done.
That's a huge operational advantage and a major flag for the exam. If the question uses the specific phrasing, updated against the last full backup, The answer is always differential. Okay, let's examine slide 10, system-level saves, snapshots, and images. We have two very different ways to save a system state here. But looking at the left side, the slide says a snapshot is not an independent backup file.
It isn't, and confusing the two is a critical error. A snapshot is just a set of mathematical pointers.
Wait, pointers?
Yeah, most modern file systems use a technique called copy on write. When you take a snapshot, the system instantly freezes the state of the data blocks. If a user subsequently changes a file, the system doesn't overwrite the original block, it writes the change to a brand new block.
So the snapshot is literally just a map pointing to the original frozen block.
Exactly, it's super fast.
So it allows for like zero downtime and instant rollbacks if data gets corrupted.
Right, but if the physical hard drive mechanism fails, or the disk catches fire, the snapshot is totally useless because those original blocks are physically gone.
Ah, right.
An image backup, on the other hand, is the sector-by-sector full file of a hard disk we talked about with DD. It takes the entire disk, operating system and all, and wraps it into one massive file that you can restore onto a brand new empty computer.
Which perfectly transitions us to slide 11, the offsite movers, remote storage.
Yeah.
Because keeping your image backups in the same room as your server is a terrible idea if the room floods.
A very bad idea.
We need to move them across the network. The slide lists the verified movers: ORSync, SFTP, SCP, and NC, which is Netcat.
Disaster recovery absolutely mandates offsite storage. ORSync is brilliant here because it uses delta encoding.
What's delta encoding?
Well, if you have a 10-gigabyte database file and only 1 megabyte of data changed today, ORSync communicates securely over an SSH secure shell connection, calculates the exact differences, and only sends that one changed megabyte over the internet.
That saves so much bandwidth. And SCP, or secure copy?
SDP is fantastic because it securely copies files between remote hosts using SSH encryption without you even needing to set up a dedicated FTP or file transfer protocol server. It's just simple and secure.
Now look at the trap warning on the right side of slide 11. Do not select DNS or DHCP when the question asks about backup or transfer solutions.
I cannot stress this enough. DNS is the domain name system. It resolves human-readable names like google.com into IP addresses.
Right.
DHCP is the Dynamic Host Configuration Protocol. It automatically hands out IP addresses to computers when they join a network. They are fundamental network infrastructure protocols.
They don't back things up.
They have absolutely zero capacity to back up or transfer your data.
Sure.
They are purely distractor answers designed to catch people who are blindly guessing acronyms.
Good to know. Slide 12 is up. Trust but verify. Integrity checks. We moved the files offsite using secure encryption, but how do we know a network blip didn't flip a bit and silently corrupt the file during transit?
That's where we use a fingerprint, also known as a hash algorithm.
Right. Encryption protects data from being intercepted, but hashing verifies its exactness.
Exactly. You run your backup file through a mathematical algorithm before you send it, and it outputs a unique character string. When the file arrives at the remote server, you run the algorithm again.
And if the source string and the destination string match perfectly, the data is undeniably 100% identical.
Undeniably.
Yeah.
It relies on the avalanche effect. If even a single comma is changed in a million-page document, the resulting fingerprint completely changes. It's not subtle.
The slide shows two main algorithms, MD5, which generates a 128-bit string, and SHA, which generates a 160-bit string or higher.
Yeah, MD5 is an older standard. It's fast, but it suffers from cryptographic collisions.
What does that mean for the user?
It means computing power has reached a point where malicious actors can engineer two completely different files, say, a legitimate system update and a virus that magically produced the exact same MD5 fingerprint.
Oh, wow. That's a huge security flaw.
It is. Because of those vulnerabilities, the mathematically rigorous SHA algorithm is actively replacing MD5 in enterprise environments.
Let's put the entire puzzle together on slide 13, Synthesis, the enterprise data lifecycle. This 5-step visual summary is everything we just talked about.
Bringing it all home.
Yep. Step 1, target your raw data. Step 2, pack it into a single stream using tar-cv-ev. Step 3, shrink it to save space using bzip2. Step 4, verify it hasn't been corrupted by generating a hash with SHA-SUMM. And step 5, Ship it securely offsite using CP.
If you can trace that flow from start to finish, you have moved far beyond just memorizing flashcards. You actually understand the functional architecture of secure data management.
Finally, we wrap up with the cheat sheets on slides 14 and 15. Exam, survival sheet, and red flags. Use these for rapid review, the absolute must-knows. The -K flag prevents compression tools from deleting your original files.
Very important.
DD is the only tool for byte-for-byte exact cloning. CPIO fundamentally requires a pipe or redirect symbol to feed it a file list. And remember the fragile chain of incremental backups versus the robust two-step restore of differential backups.
And please commit those red flags to memory. Do not fall for the fake extract command. Ignore distractor flags like -cgvf. Never try to use unzip on a .tar.gaz archive.
And when you see DNS or DHCP on a backup question,
Cross them out immediately.
keep these two slides front and center when you sit for your exams.
Tracing this entire process really puts things in perspective. We've evolved from simply trying to stuff loose files into digital cardboard boxes to relying on complex mathematical hashing to prove beyond a shadow of a doubt that our files haven't been tampered with.
It's wild how far it's come.
It is. And as we generate exponentially more data in the future, the ultimate challenge won't actually be finding the hard drive space to store it.
No. What's the real bottleneck then?
The real challenge will be the integrity verification, proving that the data we pull out of the wreckage after a massive catastrophe is exactly the data we actually saved, down to the final byte.
And that takes us right back to that black terminal screen where we started. If you're the one typing the recovery commands, you have to be absolutely sure of your tools. Thank you for following along with this deep dive. Keep practicing those commands, trust the life cycle, and good luck on your exams.